Good morning and welcome to this webinar, Soil Amendments for Environmental Remediation, presented by TDJ, manufacturers of BLASTOX. I'm Chuck Hornaday with Vados Remediation Technologies, and I'll be your host for the webinar today. Now, before we get started, I would like to just say that we're targeting a 30-minute webinar with time for questions and answers at the end. There should be a window in your top right-hand side of your screen where you can post questions. Those will be answered at the end of the call. And then also that you can mark that question private if you'd prefer for us to respond to you individually rather than read the question online. So again, thanks for attending and let's get started. A little bit of background on myself first. As I mentioned, Chuck Hornaday with Vados Remediation Technologies. I'm a geologist from the University of Wisconsin. Work with a variety of different technologies provided by different companies, including TDJ BLASTOX, and have over 30 years of experience in the environmental and construction-related field. TDJ is a Chicago area-based chemical manufacturing company serving three main markets: the foundry industry, lead paint abatement, and then treatment of metals-contaminated soils. They've treated over 1.5 million tons of waste that with this particular BLASTOX chemistry. JCE, or J. Carpenter Environmental, is a distributor of the TDJ products based in Wisconsin. They are currently celebrating their 100th year. They provide a variety of different waste treatment and pollution control products and distribute our products throughout the northern Midwest and Northeast U.S. Vados Remediation Technologies, as I mentioned, that's me, and I'm a manufacturer's representative for TDJ BLASTOX. Now, our outline for today's presentation is to talk about soil amendments for environmental remediation, and these amendments may be used in a variety of different ways, including hydraulic control or low permeability barriers, control of NAPL migration, passive treatment of dissolved phase contaminants, a few other typically available amendments, as well as in-situ and ex-situ treatment of metals contaminated soils. Starting out, we'll talk about hydraulic control or creation of low permeability containment barriers. This is done often with bentonite. Bentonite is an ore with the main ingredient being clay montmorillonite. It was formed as a result of the aqueous deposition of volcanic ash in what was once the western interior seaways. The highest quality sodium bentonite is now found in the Black Hills region of the western U.S. Bentonite is unique in that it swells significantly when hydrated. Bentonite can swell up to 15 times its original volume. So it's this swelling pressure and the clay platelet morphology that allows the bentonite to provide a very low permeability. Bentonite has also been shown to have metals attenuation capacity, making it ideal barrier for metals contamination as well. Now, low permeability liners and covers can be constructed with the use of bentonite as a soil amendment. Bentonite can be added to soil at rates of, depending upon the initial permeability of the soil, but rates may be up to 15%. It can be either blended in place or mixed with a pug mill and then placed and compacted and covered. Bentonite is also used in hydraulic control of groundwater, typically in the application of a slurry wall. A slurry wall is a non-structural, low permeability vertical barrier that's designed to reduce the flow of groundwater. So the intent is to contain contaminated groundwater, say from migrating off-site. The picture here on the right shows a slurry wall being constructed, a bentonite slurry, which will then be backfilled with a low permeability backfill containing bentonite and soil. This low permeability wall would then be used to control the migration of groundwater. Some considerations for constructing these walls includes the use of an appropriate API-grade bentonite, considering whether mobility of organic contaminants is also an issue in the construction of the wall, and also the effect that the wall would have on the hydrology or the groundwater flow, and the potential to redirect the contaminated flow. Bentonite is available in a variety of different particle sizes, powder is commonly used in the construction of slurry walls and also in in-situ stabilization applications. And granular bentonite is used in mixing with soils because of its less dusting, again, able to achieve low permeabilities, with bentonite itself having a permeability of at least 2 times 10 to the minus 8 centimeters per second. It should also be noted that bentonite is really intended for use only in fresh water, as salt water can have a very serious effect on the ability of the bentonite to swell and therefore provide a low permeability. Now, one consideration for control of contaminants is their presence in the non-aqueous phase liquid form. Non-aqueous phase liquids might be either denser or lighter than water. NAPL may be pumped off the groundwater surface or can be controlled with hydraulic barriers and or passive treatments systems such as PRBs. Dense non-aqueous phase liquids such as coal tar or creosote may be difficult to predict their migration and also difficult to reduce their mobility. Passive treatment of these types of materials or in-situ stabilization is most commonly used. A permeable reactive barrier is installed across the flow of a contaminated plume, and as groundwater flows through it, the PRB contaminants are either degraded or retained by the reactive or sorptive material in the PRB. Now, that material might be a granular activated carbon for dissolved phase contaminants, or biomass, wood pulp, or char, a variety of other organic materials, as well as a modified clay called organoclay. Organoclay is a granular filtration media which is effective for removing oils, grease, and non-aqueous phase liquids and other dissolved phase, high molecular weight, low solubility organics. It's capable of removing as much as 0.5 pounds of organics per pound of media used. So this organoclay, as mentioned, is a filtration media permeable to water, will allow water to pass and sequester contaminants as they pass through with the water. So it's used in applications such as a permeable reactive barrier, as an additive to in-situ stabilization applications. It's used in capping of contaminated sediments and shoreline NAPL seep control, and is also available in the form of mats, which are large rolls that are able to be deployed in a uniform way. An example of how organoclay can help to reduce the NAPL mobility is shown in these pictures. We see on the top left a coal tar droplet that's placed underwater but on top of a layer of organoclay. And after a relatively short time, you can see how the organoclay has fully absorbed that coal tar. And what that I think is a good illustration of is the ability of this organoclay to reduce the mobility of the organic contamination or NAPL. Some other ways that groundwater or contamination might be treated using amendments include a passive groundwater treatment or an in-situ treatment of groundwater. This is commonly done through injection of amendments. One such amendment is something called Bioavailable Absorptive Media, or BAM. This is pyrolized recycled cellulosic biomass, and it has a very unique pore structure, as the SEM image shows in the top right-hand side. This very high porosity increases the surface area and sorptive capacity of the BAM, allowing it to sequester contaminants and then leave them available for degradation or natural attenuation. This material is available in a variety of different particle sizes. The picture on the bottom right showing it being used in a granular form as a soil amendment for ex-situ treatment of some organic contaminated soils. And it's also available in a very finely milled powder, which can be used for injection applications. That might look something like this. You can see the BAM material injected through some points into the subsurface below the water table, creating this permeable treatment zone where the dissolved phase contaminants in the groundwater plume will pass through and then be sequestered by the BAM. The material is, as I said, very finely milled and easily injectable. It's done through a series of sequential injections into the treatment zone, and the zone will then remain permeable and capture these dissolved phase contaminants. There's been numerous pilot scale and full scale applications of this material having been used. A few other media to talk about briefly. One called MicroBoost is something new on the market. It is a dry, granular, biologically active media, which provides a verifiable population of hydrocarbon degrading microbes. So what we have is a calcined clay that's been treated with 21 petroleum degrading microbes, again allowing you to have a verifiable population of biologically degrading microbes in your remediation. It's designed to create an active zone or treatment zone for biological degradation of petroleum contaminants. Again, the idea to create a passive zone where groundwater would pass through and the zone would sequester and then treat the contamination. Another treated clay showing promise these days is a material called Fluorosorb, which is designed for both filtration applications and in-situ stabilization applications of PFAS compounds, one of the new and emerging contaminants hitting the industry. Now let's move on to BLASTOX for metals treatment. BLASTOX is a material which may be used for either ex-situ metal stabilization or in-situ solidification stabilization applications. So an ex-situ application would include a stabilization of this metals contaminated soil prior to it being excavated and disposed of, which would then render the waste as non-hazardous and able to be reducing the disposal costs. In-situ treatment of metals contaminated soil may also be done to reduce the leachability of these metals into the groundwater and also reduce the bioavailability of the metals to sensitive receptors. So what is this BLASTOX? It's chemistry is a complex calcium silicate. It's a very fine granular material designed to target lead and cadmium. It's available from TDJ in packages of 70-pound paper bags, 3,000-pound super sacks, and in bulk. And again, it's also available in a couple of other formulas which are designed to target arsenic, chromium, and others that may need to be reduced to a lower valence state prior to complexing. So how does BLASTOX work? Actually, BLASTOX works in 3 different ways. There's 3 different mechanisms which I'll explain. First, it works by releasing an alkali, adjusting the pH, which slows metal dissolution. Our target is to put it in a pH range of about 8 to 11. This next slide shows solubility of metal hydroxides, and you can see that when lead is in that range, that 8 to 11 range, that the solubility decreases by at least an order of magnitude. So significant decrease in solubility. That mechanism alone is enough to allow the lead contaminated soil to meet a TCLP requirement potentially. The second mechanism is through conversion of the metal to another compound, for example, a lead silicate. This would be through addition and substitution reactions, and again, this is a less soluble form of that metal, again rendering it able to not leach out of the soil. And then the third mechanism is through micro or macro encapsulation. Essentially, what we're doing here is by reducing the permeability of that treated soil, will reduce the flow of water through it and therefore reduce the amount of leaching. So again, multiple safeguards, multiple methods of mechanisms for function allow a reduced liability. Now, what does BLASTOX look like? Actually, BLASTOX, as I mentioned, is a fine-grained granular material shown in the center. But we do also have a coarser grain and a powdered grade of material typically used in other applications. Here's an example of an ex-situ stabilization project using BLASTOX. This was a former auto scrapyard where the surface soils were contaminated with lead. This contaminated soils were consolidated into a stockpile and then having tested out at over 100 milligrams per liter of leachable lead, we treated the soil with BLASTOX at the rate of 3% using BLASTOX 215. TDJ provides complementary treatability testing so that we can verify the add rates. So typically, if you know your leachable lead concentrations, we can begin with a expected treatment rate or dosage rate, and then test it to verify that it will work. So in this case, all soil was treated on site, and no special waste permit was required for treating the characteristically hazardous waste. Finally, after treatment and passing of the tests, the material was disposed of in a Subtitle D landfill. Here's an example. This video here will show the mixing of the stockpiled. Basically, they took the stockpiled material and placed it in this mixing pad, and then used this rotating head on the front end of the excavator to mix in the BLASTOX. So the BLASTOX is the light gray material, and the rotating head is mixing it in. So we know that we can treat metals contaminated soil to pass a TCLP test. But what about the long-term stability of BLASTOX? We know TCLP test is used to determine if a waste is either hazardous or non-hazardous, but other test methods can be used to determine the long-term stability of metals treated soil. So that might include the MEP method 1320. In this test method is designed to simulate leaching from repetitive precipitation of acid rain. So the test method uses a pH leach solution of 3 versus 4.88, which is typical for the TCLP. It is designed through this repetitive testing and leaching. It's designed to eliminate that buffering capacity that might come from a simple pH adjustment. And so, as mentioned, the multiple treatment mechanisms that BLASTOX employs allows for that material to still do well even under this testing condition. Some other chemistries that are also used for metals treatment are more simply a buffering agent and usually won't fare as well using this MEP test method. So who's tested it using the MEP method? Several different tests have been conducted by different federal agencies, including the US EPA, tested 46 different combinations of samples and concluded that the BLASTOX waste exhibited long-term immobilization and durability. The Federal Highway Administration also tested the material using the MEP method and concluded the BLASTOX stabilization was very effective, and the U.S. Department of Defense concluded that there is no laboratory evidence of problems associated with the long-term durability. So again, 3 very good testimonies to the performance long-term of BLASTOX materials using the MEP method. How do you know how much BLASTOX to use to treat your metals contaminated soil? We can look at historic dose rates based on the leachability or the amount of leachable lead in the soil. Typically in the lower range of 25 to 25 milligrams per liter, we would add about a 3% dosage rate. And for higher leachability, we might add as much as 5% leaching, 5% dosage rate. So I should mention that BLASTOX provides these studies complementary treatability testing to verify the appropriate add rate. It's ideal to have split samples of samples that have already been collected on site so that we can verify the total lead and leachable lead from the samples untreated, and then we'll treat the sample up and verify in fact that the dosage rate is effective at treating the sample. How do you calculate that amount of reagent that you need? Simply convert the soil volume to mass by either using a conversion factor. We typically use 1.4, which equates to a mass per unit area of about 105 pounds per cubic yard. Then you divide that mass by the treatment rate. So for a 3% dose rate, you would divide it by 1 minus 0.03 or 0.97, and that will give you the total mass of soil and reagent. From that, you subtract the mass of the soil. So as an example here, we have 10,000 cubic yards of soil with a 3% add rate. To determine the amount of reagent needed, you would take 10,000 times the 1.4 conversion factor to get 14,000 tons of soil. To that 14,000, you divide it by 1 minus 0.03 or 0.97. Excuse me, you would divide it by 0.03 and you would get 14,433 tons. So 14,033 tons minus the actual mass of the soil shows that you would have 433 tons of reagent needed to treat that soil at a 3% rate. How is it mixed? In general, BLASTOX is available in either bulk bags, 70-pound paper bags, or by bulk delivery. It must be mixed thoroughly with the soil in order for it to effectively treat it. There is no residence time or curing time that's necessary in order for the BLASTOX to become effective. It can be tested immediately after the samples are collected. Soil may be mixed with any type of heavy equipment, including continuous feed systems such as a pug mill. In-situ treatment applications would be one where the soil is treated prior to it being excavated. You would apply BLASTOX to the top of the soil at the appropriate rate or dosage rate for a specified lift. And that lift should never exceed 4 feet. Once it's been applied, you can mix it with a backhoe or an excavator with that mixing head, similar to what I showed in the video, and ensuring that the soils are turned over 5 or 6 times. After mixing, the material is excavated and then stockpiled and held for testing results and then disposed of. Another method might be a situation where you have all of your soil in a stockpile, in which case you would establish a standard batch size and calculate the amount of reagent needed for each batch. Move that soil to a mixing pad, apply the BLASTOX, mix it in properly, and then take samples for testing, holding the treated soil in another stockpile until the testing passes. Some other considerations. So we've talked about applications where the treated soils are then excavated and taken for disposal as non-hazardous waste. Other applications might include treating soils in situ and leaving them on site, which may be a possibility depending upon local regulatory requirements. We always encourage you to become very aware of those requirements that might be needed to ensure your project is compliant. BLASTOX can be added either to cement-based mixes to improve the leachabilities of the metals from that solidified soil mass, or they could be mixed into the soil without the cement, which would achieve a much lower compressive strength. Different testing methods might need to be considered or used to evaluate the appropriateness of the treated soil for being left on site. So in addition to TCLP, the SPLP or MEP methods may need to be done. Evaluation of the bioavailability or RBA using method 1340, which is the standard operating procedure for in vitro bioaccessibility assay, may also need to be done. This is a method of ensuring that the treated lead or the treated metals have in fact become less bioavailable and are now suitable for being left on site. There is certain EPA data that indicates that certain forms of lead, such as lead silicates or lead oxides, are less well absorbed into the body than other forms. Again, we encourage you to do more research on this prior to employing an in-situ stabilization application. how much money can be saved by using BLASTOX? BLASTOX has a cost of about $300 per ton. In addition to that, so using a 5% dosage rate, that would equate to a $15 per treated ton of soil. Assuming a disposal cost of $40, that's a total cost of about $55 per ton. If the material is not treated, taking it to and disposing of it in a hazardous waste landfill would likely have a cost of $200 per ton. So a significant saving of $145 per ton could potentially be achieved. It's important to recognize the assumptions here, and that is that the freight of the material, the BLASTOX material to the site, has not been included. However, neither has the waste freight to the landfills, and hazardous waste sites are generally much further apart than non-hazardous waste subtitle D landfills, so the cost of shipping to a hazardous waste landfill would likely be much higher than disposing in a non-hazardous waste landfill. And finally, the costs of mixing the reagent is also not included. Regardless of those factors, clearly using BLASTOX can help save money on the disposal of metals-contaminated soils. Here's a couple of projects that we've done using BLASTOX to give you some idea on the treatment dosage rates. A former auto assembly plant in St. Louis had about 10,000 tons of lead-contaminated soil, which tested out at a leachable lead of 100 milligrams per liter. We used 4% treatment dose and were able to successfully treat that soil. Another property, an abandoned industrial property in Chicago area, had about 4,000 tons of soil also contaminated with lead, which tested out of leachable lead concentrations of 6.3 to 189 milligrams per liter. Also used a 4% dosage rate and were able to successfully treat that soil. And finally, a site in Texas, in the Twin Cities of Minnesota, a Superfund site with 1,500 tons of soil contaminated with chromium and cadmium. The waste tested greater than 12 milligrams per liter for chromium and greater than the 5 milligram per liter threshold for cadmium. And we stabilized this waste with a 10% add rate of a specially formulated version of BLASTOX we call ChromeTox. And so again, able to successfully treat that waste to below TCLP limits and dispose of it as non-hazardous waste. So with that, I'd like to thank you again for attending this webinar, and we hope that we have been able to provide you with some information that would be useful for you. And with that, we'll open it up for questions. Thank you.